Okay. Pay attention now. This is going to be the hard talk. So, I like functional programming. And the thing about functional programming is that it tends to be a little complicated compared to what you're normally used to, which is good. Because, you know, there is a thing called a hipster. Do you know what a hipster is? I'm sure you do. So hipsters really enjoy feeling a bit superior to you. So obviously, a programming hipster will be a functional programmer. Because there's this gigantic vocabulary of terms that are quite difficult to understand, and that also sound very, very difficult, that they just employ, regardless of whether they necessarily understand them themselves, to make you feel stupid. And so today, I'm going to try and do something about that. I'm not going to show you why functional programming. I'm not going to show you the how of it. I'm just essentially going to show you what. So I'm going to just run through some of the essential words and some of the concepts. I'm going to show you how, at least one example of how to do each. So you have a basic understanding, at least enough that you can start employing these words to confuse your coworkers and make them feel more stupid than you. All right, let's get started. So there are essentially four great paradigms of programming. You have, of course, the systems programmers, the very imperative low-level languages, like C, like the kind of language you will use to write an operating system, or regular expressions. Actually, the guy with a beard invented regular expressions, and the guy with a beard invented C. So now you know that. Of course, there's the object-oriented programmer. This isn't necessarily a paradigm of its own, but once you go as far as languages like Java has done, it is really all about the object. You can't, even though Java is essentially an imperative language, it's just objects, essentially classes. And the object-oriented programmer is here pictured in his native habitat. I'm sure you're familiar with it. I know I am. Of course, there's the functional programmer. The functional programmer is smarter than you and enjoys making you aware of that fact. Functional programming is arguably a distinct term from imperative programming, even though some functional languages are also imperative. Finally, there is the logic programmer, the declarative relational programmer. And we're not going to go into that paradigm. I don't think humanity is quite ready for this yet. Perhaps in a few hundred years we can get back to that. But in essence, we are concerned with two of these paradigms. We have the functional programmer, with a lovely moustache, I might add. And he is better than you, he knows it. And then there's you, the muggle. The object-oriented, Java-oriented, whatever you like. You could use some training, and that is my intention today. So, there is a language called Haskell. This is essentially a wellspring of confusing terminology. It is created by academics, for academics, and you're not meant to understand it. So the reason Haskell is so opaque to the common man is that it is essentially derived from a branch of mathematics called category theory. This is an interesting topic on its own, but essentially category theory contains a lot, like, I'm not going to say millions and millions of strange and confusing words, but at least they can be combined in many interesting ways. So category theory is the gold mine that we're going to harvest today. So let me give you a brief historical overview before we get started on the code. There was this guy called Alonzo Church. He invented something called the lambda calculus. And there's this guy called Haskell Curry. You might remember his name. The language Haskell is named after Haskell Curry, who kind of helped with the lambda calculus. This is the lambda. That is essentially what the lambda calculus consists of. It is a calculus that only has functions. It doesn't even need. It has symbols as well that you can assign functions to, but you don't need things like numbers and other filthy things to use the lambda calculus. That's for like beginners math. We don't use numbers in proper math. So the super lambda brothers. In fact, Curry. He liked the lambda calculus the way it was, but Church decided we kind of need to introduce types to this. And at that point, the lambda calculus actually became useful, as we are about to see. Because by accident, there was this guy called John McCarthy, who created his own version of the lambda calculus. And one of his students decided, just for the heck of it, to try and write an interpreter for that calculus on a very old computer. This was in 1958. And it turned out the lambda calculus, McCarthy's version of it, was actually a programming language. It wasn't intended to be. Programming languages at the time looked more like very, very old Fortrans and were quite horrible. But by accident, these guys discovered essentially a language that is pure mathematics, and that language is called Lisp. That was the first functional language. And let's just dive into the code. So the core principle of functional programming is that functions are first class, which means that functions are values that can be passed around, just like numbers and strings and other values that you're used to. So let me just show you what that means. Here's a function, hello. Notice, by the way, this is not JavaScript. This is very close. It's actually TypeScript, which is essentially Microsoft's typed version of JavaScript. I figured that as this gets more complex, you're going to enjoy actually seeing type signatures, which is going to make it a bit easier to follow. What this means is that we have a function hello which takes no arguments, and it returns an argument that has to be a string, or there's going to be a compilation error. And as you see, this does return a string. And so running that means we get hello every pony. We are, by the way, entering Ponyland, so prepare yourselves. And this is actually how I discovered functional programming on my own, a bit by accident. Because in a language like JavaScript, you can evaluate the function without calling it, without the parentheses at the end. What happens then is that you get a function. It returns a function. It returns the hello function, in fact, which means the function is actually a value. You can do things like assigning it to a different variable. So if you now call the new variable, you call the same function. And more interestingly, you could write functions that take functions as arguments. Function. Right. This means that func should be a function. And what this does is simply call that function. So we can go and pass the hello function to that. Oops. Right. So the rules of live coding is if you spot a typo, you tell me, otherwise it's all your fault. Okay? So this one's a new. Notice, we pass the function into the function that calls the function, and it works. Yay. First class functions. That's amazing. Okay, moving on. This is a more difficult word, which I like this one. A functor. In some languages, a functor just means a function, but that would be too easy in category theory. A functor is a collection of x that can apply a function f from x to y over itself to create a collection of y. Right? This is obvious. So I'm just going to show you. You might find this familiar, in fact. So we have a function caps, which just takes a string, returns a string uppercase. And we have this map function, which is part of the functor. The functor, in fact, is, and this is what's great about category theory, because the terms don't just necessarily mean one thing, they mean a collection of things. And in this case, the functor consists of a collection value, which in our example is going to be a list, but doesn't have to be. And it consists of the map function, which I'm now going to implement for you. The map function, you will notice, takes a function that takes one argument, that can be anything, and returns another argument. Oh, well, that is an argument. It returns something that can be anything. And it takes a list, because in this example we are using a list as the collection value. And it also returns a list. So let's just implement that. It's going to be easy to follow, I hope. So we start with a variable that is an empty list, and we need an iterator, and we have a for loop. And so what we essentially do is that we walk through the input list, which is called list, and we append, we push, the result of calling func on the current value for each element of the list. So we construct a new list that is kind of mapped through the input function. And we just return that. And so observe, we have ponies. These are ponies. These are loud ponies. So what we did is we essentially have a function that takes another function and applies that function to each element of the input list. You might recognize this because this actually exists in JavaScript already. In fact, on all array objects in JavaScript, you have this map function already. So we could just go, this is native JavaScript, and it eats the same thing. So that is the functor. Bonus points if your input function, the function that you're applying, returns something of the same type as the value you put in. It is called an endo functor, which is even more complicated. Or at least it sounds fancy. So, moving on. So there's also another operation that kind of goes hand in hand with this. It's called filter. The idea is that instead of a function that mutates or changes the input, we just have a function that returns true or false. And if it returns true, the value gets to be in the new list. Otherwise, it does not. So, obviously, instead of just calling the function, we just do an if statement. So func of list I, if that is true, or truthy, which can be anything really, we just push the value unchanged onto the new list and we return it. And so we have the toCool function. That simply checks if a pony is too cool to be in just any list. And obviously, as we can see, Rainbow Dash is too cool for that. So, if we then filter ponies in too cool, we will observe that Rainbow Dash is not present in that list. If, in some bizarre universe, Rainbow Dash is the only pony that is not too cool to be in this list, obviously, we get a list with just Rainbow Dash. That's simple filtering. Now, reduction. This is the last member of the map filter reduce family that you see quite often in basic functional programming. Suppose you have an add function that takes two numbers, or whatever, really, and adds them together. JavaScript is quite liberal with what you can add. So we're going to implement the reduction, and the idea is that we now have a function that takes two arguments, an accumulator and the item in the list that we're iterating over. So we have to start, we're going to produce a result, which is an initial value, which is now being passed in, along with the function and the list. This is supplied by you, and it usually has to be something that makes sense. So an iterator. And so in this case, we are going to assign to result the result of calling func on result and the current item. and we just return result when we're done. So this has the potential of not returning a list, but a computed value, which the most basic example of this is if we do reduce on the add function and a list of numbers. And let's say the initial value is 0. What's that going to do? Care to guess? It's going to compute the sum of this list, which happens to be 50. Suppose we do the same with ponies, because you have to try and do things with ponies. That simply concatenates, because the plus operator in JavaScript concatenates strings. Right, that is well and good. This gets more interesting when you realize that in category theory, this is not called a reduction. It's called a catamorphism. I'm so sorry, you guys are trying to translate this for the deaf. It gets worse, don't worry. So, the interesting thing about the catamorphism is that it is actually, the map is actually a special case of a reduce, which I'm now going to show you. Suppose that instead of the caps function, we have a shouty map reducer, which, because this is a reduce function, it takes an A, which is a list of strings, because that's what we're going to accumulate, and a B, which is a string, which is the element, and it returns a list of strings. And so, quite simply, we are going to concatenate a list containing the result of calling, b.toUppercase, which is what the caps function essentially did. Is that balanced? Yes, it's balanced. Okay, so if we do reduce shouty map reducer, I wish I'd come up with a shorter name. It's the Java developer in me, I suppose. On ponies, and the empty list as the initial value, because we're going to construct a new list out of that. This should do the same as the map. So map is a special case of reduce. This is nice to remember. Higher order functions. Actually, any function that takes another function as an argument is a higher order function. But more interestingly, a function can return a new function, essentially a function factory or a function factory if you're a Java developer. Let me show you. I thought I'd generalize the case of how map is really a reduction by making a function that takes a function that is suitable for mapping and turns it magically into a function that is suitable for reduction. Are you with me so far? Is this getting complicated? Nah. You're JavaScript developers, you're totally smart. So, we take a function that looks like a map function. It takes one argument and returns another. And we have to turn this into a function that takes two arguments, which is required for the reduction. And it does pretty much the same thing as the shouty map reducer, except that it concatenates func of B. And that should do it. So now we should be able to reduce, let's just try the old one first. Shouty map reducer on ponies, an empty list. Still works. So now let's call map reducer on caps. And use that as our reduction function. This should actually turn caps, which is not compatible with reduce, into something that is. Yay, it works. That's a high order function. So, moving on. Combinators. Combinators are very interesting. There's this huge branch of mathematics that is called combinatory logic. Of course, invented by Haskell Kareem, because everything usually is in the end. And the idea is that you have a set of combinators, which are essentially functions that change other functions in a fixed way. You have things like the Y combinator, which you might have heard of, which is a combinator for getting you funded. and others like the S combinator and the B combinator. And I'm not going to show you any of them. I'm going to show you some very stupid combinators, just as an example. Suppose you have a square function. Square. So square of 5 essentially returns the square of 5, which is 25. So I'm going to introduce you the 3 combinator. I just made that up, by the way. And 3 takes a function which is a function that takes a number and returns the number. And what it does is it returns a function, it creates a function. This is the function factory, or a high order function, which also takes a number, and it returns the result of calling that number plus 3. So the 3 combinator essentially mutates a function that operates on one number into, well, let me just show you. Let's see if you can guess what it is. So running the 3 combinator on square gets us a function. And if we call that function with 5, what are we going to get? 28. Let's see. 28. Yay! So that was perhaps the most useless combinator you have ever seen. Let's try something useful, or at least a little more useful. Suppose we have a JavaScript object called Pinky. And we have a function pony type, which operates on an object like Pinky, which has a name and a type property. So we can go pony type on Pinkie Pie, and that's going to return Pegasus pony. Does that look right to you? Does it really? You're kidding me. You should know this. Pinkie Pie is not a Pegasus pony. She's an Earth pony. What, are you stupid? So, okay, that's fixed. Now I know there are no bronies in the audience, because a brony would not have stood for this. All right. Now suppose that we have another pony, Rainbow Dash. Suppose that Pinky came out of a database query. You know, those queries can sometimes fail. And Rainbow Dash is obviously too cool to be returned by any other database query. So I suppose that Rainbow Dash has been initialized to be 0. Oh, sorry, null. Because the query failed. What happens if we go pony type on Rainbow Dash? We get an exception. That is not good, because that is going to halt your program unless you catch the exception, which you probably should be doing. Oh, fine. Let's instead introduce another combinator. Let's call it the null combinator. Let's write a function null check to apply that combinator. So it takes a function, and I'm just going to skip the signature because you get the idea. And it returns a function that takes x, which is going to be the pony. And if x is triple equals null, because otherwise Douglas Crockford is going to be mad, we return null. Otherwise, we return the result of calling func on x. Now, null safe pony type equals null check on pony type. And null safe pony type on Rainbow Dash, instead of throwing an exception, returns null. So we have created a null check combinator essentially, which might be useful. What you probably should be doing instead is dealing with the error when this happens, instead of just happily ignoring it. But that is a topic for a different talk. Moving on, composition. This is essentially how you do code reuse in functional programming. Because composition allows you to compose functions together to create a kind of a processing chain. Suppose we have the caps function again, and we have a function hi, which says hi. Hello, pony. Oh, free pony. Now, suppose we call caps in that. Hello, pony, very loud. This can be automated. We can create a compose function that takes a function 1 argument to anything, and a function 2 with the same signature. return a function that takes this argument, which can be anything, and essentially calls func2 on func1 on x. So, assuming that we compose high and caps together, that's essentially going to be what we're doing above. That gets us a function. Shout high. Calling that on every pony yields the same thing. And so we have composed these two functions together. Very useful. This is going to be a practical example, but first I want to talk about applicative functors. I think we have... Actually, I'm going to rush through this, if you're okay with that. I should probably just have skipped this part, but it is so adorable, the end result, that I'm going to try and do it anyway. So an applicative functor is essentially the same as a functor, except it also has an applicative map function. This is my implementation of that. So I'm not going to type it out for you. It gets complicated because essentially the idea of the applicative map is, in the case of a list, is that you combine things together in all possible ways. Which means that you can use more than one function, you can have more than one set of arguments, and in fact, I'm just going to show you what happens with more than one set of arguments in this case. So we have ponies. We want more ponies. Now, you have a chance to redeem yourselves. Can you name some more ponies? Applejack? No, that is the set of ponies. We want specifics, we want implementations. Rarity, and, oh, come on. Fluttershy. Right, those are the main six. And let us suppose that we have a function hug, which takes a pony and another pony. And of course, pony 1 hugs pony 2, because ponies like to hug. So let us try the applicative map on that. It takes actually a list of functions, but we're just using the one, which is hug. And it takes, as I said, any number of argument lists. So we pass in ponies, and we pass in more ponies. And what happens is that every pony from the first list hugs every other pony from the second list. So all possible combinations of the two sets of ponies are exhausted. And that's kind of adorable. And that is also applicative functors, which is a very nice, long, complicated word. So enjoy that. Currying. I'm using like the lamest possible illustration for currying available, ironically, of course, which reminds me, why am I doing this talk without hipster glasses? There, do I look less mainstream now? Great. So currying. Currying, as you can imagine, is named after Haskell curry once again, because everything is. And it is the act of transforming a function of several arguments into a chain of functions of one argument that will yield the same result when called in sequence with the same arguments. Like so. The function signature at the bottom is probably easier to understand. What it means is that suppose you have a function of 3 arguments. Currying that function means that you get a function that takes one argument, that returns a function that takes the next argument, that returns a function that takes the last argument, and that should do the same thing. I know what you're saying, why is this useful? I'm going to show you later. So, interestingly, it is named, as I said, after Haskell curry, but it turns out that he wasn't the one to discover this. There was this guy called Moustache, who essentially lived in Stalin's Russia, who discovered it like 3 years earlier, and nobody really knew about that. So Curry discovered it independently a bit later, which leads some people to insist that it should be called Schönfinkling in all fairness. So, if you hear somebody talk about currying, correct them. It's Schönfinkling. Give credit where credit is due. Right, so this is a curry function. Huh? I'm going to call it currying for now, because I'm not going to rewrite the code. I'm not even sure if Unicode characters will work. So we have an add function. The add function takes any set of numbers. Right. And we have the curry function. I'm going to curry the add function. And I do that by using add as the first argument. And notice the second argument is arity. That's an interesting word. It is not a pony, that is rarity. Arity simply means the number of arguments a function takes. So a function of arity 3 takes 3 arguments. And since in JavaScript we don't necessarily know how many arguments a function takes just by looking at it, we have to specify that manually. So currying add with 3 arguments means that we get a function, and we call that function with the number 1, gets us a function. We call that function with the number 2, gets us another function, and now finally we call that with the number 3, the third argument, and that yields 6, which is what the add function does, except we've split it up. So that's currying. Why is that useful? The most common case of currying, incidentally, also the thing that is most commonly confused with currying itself, is called partial application. Now, if you notice somebody doing partial application and calling it currying, do correct them. Partial application is not currying, it's just a special case of it. Or Schoenfinkling, if you like. So what essentially we can do is create something called 1 and 2 and, just to use a stupid example, and assign that to the partial application of adds with 1 and 2. So we kind of specify the first arguments of a function, and we create a function that has those arguments pre-filled. So we can just go 1 and 2 and this is the $1,000,000 question. What does this yield? 6. So this is actually another component of creating these I don't know what to call them, processing chains, along with composition. Kind of a central tenet of functional programming, I think. Moving on, because we have the big one left. Hope I have time to do that. Yes, I think we do. So, monads. Yes, I'm actually talking about monads at the JavaScript conference. I went there. What is a monad? Well, monads were originally invented by Gottfried Wilhelm von Leibniz, the German mathematician and philosopher. And if you think you know what monads are in category theory, they have nothing to do with Leibniz monads. I just put Leibniz in there for the heck of it, to be honest. In a more practical sense, monads were introduced into Haskell, which kind of depends on them, by the Kryptonian mathematician Philip Wadler. The only person I didn't have to Photoshop for this presentation. Thank you, Philip. So, a monad, essentially, is something that obeys the 3 monad laws. And these are not the 3 monad laws. The 3 monad laws go like this. The first monad law is you do not talk about monads. The second monad law is you do not, yeah, you get the idea. And there is some truth to this, because if you ever tried reading a monad tutorial, you'll notice that people who understand monads are obliged to then try and obscure the enlightenment they have achieved by writing confusing monad tutorials and putting them online. There are millions of them. Don't read them. They're not going to help. And the best part about monads is that they are also known as Kleisli triples. Oh, I love that word. Kleisli triples. That sounds so pretentious. It's adorable. I'm going to show you a use case for monads. And perhaps you will understand what they are in the process, but don't count on it, because monads are super complicated. So we have a list. This is essentially an HTML document. So we are seeing a list of ponies and sublists with their corresponding elements of harmony. If you don't know what an element of harmony is, then go watch My Little Pony. So the exercise is we are going to take that list and we are going to extract the elements of harmony out of that list, which means that we are going to need a function that essentially digs out child nodes from the DOM tree. And we have the function children for that. It takes an element and it returns a list of child elements. So if we extract the ponies list from the document and call children on ponies, we should get the ponies. Now, how to get at the elements of harmony from that? Remember composition. We can use composition for this, right? We get the children of the children, the grandchildren. So we can compose children together. See if that works. It is not, because what comes out of the first children call is a list. And the second children call expects, as you can see, just one element. Enter the list monad. This is perhaps one of the easiest monads to understand by example. But the problem is, you don't really understand monads just by understanding the list monad. The beauty of monads is you can keep getting specific monads, and you don't really quite grasp what monads in the general sense mean, unless you're a mathematician. Anyway, so a monad consists, in its essence, of two functions, unit and bind. Unit simply takes a value, which can be anything, and returns something suitable for composition, which in this case means a list of anything. And that is quite simply a list with one element, the value we pass in. So that is the first part of our adapter. Bind is way more complicated. The idea is that it takes a function that looks like children and adapts it to something that is composable, which means that this element, the first argument, has to become a list of elements, which means value anything into a list of anything. That is the input function. And it should return something that takes an argument list, which is a list of anything, and returns a list of anything. This is the composable function. And so obviously we're going to be using higher order functions. A list of anything. So this is going to look a bit like what we did for the special case of the reduction. We are going to have a list that starts out empty, and a counter, and a for loop. And so we just concatenate onto the out list the result of calling that function that we're passing in on each element of list, because we expect that to return a list, hence the concatenation. And we finally return the result of doing that, which means that we can now apply the list monad to this. First, we have to convert the input value into something suitable for the list monad, or the resulting bound function. So we call unit on ponies. Ponies is just one element, remember? And we call bind on the function we want to compose. So, almost there. Now it doesn't break, because we have adapted the children function for composition, which is essentially what the list monad does. So, why isn't this working? You're all HTML experts. You tell me. No? Okay. Well, the thing is, the way you make sublists of a list is that inside each element, you need to not have a sub-element, you need to have a sublist, which is what we're seeing. We're seeing lists inside each element. So, in effect, we don't want the grandchildren. We want the great grandchildren. And lo and behold, These are the elements of harmony, and that was the list monad. You now know monads. Congratulations. Finally, oh, I see we are actually out of time, but I'm going to run a little bit over. Finally, Haskell doesn't stop there. Haskell is just an endless fountain of confusing language. Like, this is my favorite, the absolute most awesome morphism you've ever seen. This is a real thing in Haskell. It's called the zygohysomorphic prepomorphism. Honestly, this is in Haskell. This is all the documentation you get from the Haskell wiki, along with a code example. So you're expected to get that. And if you don't, just know that zygohysomorphic prepomorphism is a prepomorphism with both zygomorphic and hysomorphic properties. Okay? Great. So if even that isn't enough for you, there is the course Logic Programming. Thank you very much. And now for the interesting part. Are there any questions? There are actually questions. You want to go over there? Because you got to say something to get the Firefox phone, right?
Okay, so how do one transform oneself from an object-oriented shirt-wearing guy into a hip and functional programmer? Where do you start?
Oh, you just start by learning these words. Just go talking about catamorphisms and any kind of morphisms. Can I just put in the zone for that? Don't worry. Just make people believe that you understand this thing. You don't actually need to understand it. Nobody understands monads, except maybe Philip Wadler.
Yeah. Question. You made a function that made the ponies hug each other.
Yeah.
But to hug, you need hands. So
you don't.
There's a bug in your code.
You need arms. Or forelegs, perhaps. I don't buy that. I've seen ponies hug. You need to watch more My Little Pony.
So, Bodil, is there any chance for non-functional languages to succeed?
Oh, absolutely not. They're too easy to understand. Actually, that is a lie. Functional programming doesn't have to be difficult. It's just that Haskell likes to make it difficult. And certainly, non-functional languages, if you want to call them that, can be very hard to read. If you've seen legacy Java code bases, you know this. Okay, so who am I going to give the phone to? You think that by trying to make up lies about ponies, you get the phone? You want to admit when the ponies can hug? Will you admit that ponies can hug? Then you get the phone.